Welcome to the presentation of the Bruno Rossi Prize and the lecture that goes with it. I'm Joel Bregman. I'm chair of HEAD. And for those of you who are unfamiliar with Bruno Rossi, he was really the grandfather of high-energy astrophysics, an extremely prominent physicist in the 20th century, fundamental in the study of cosmic rays, the establishment of many of the techniques that are used in high-energy physics and astrophysics, including development of various parts of space physics. And it's in his honor that we award this prize every year to scholarship of great distinction. And this year, I'm very pleased to be able to award the Bruno Rossi Prize to Marco Tavani and the Agile team for the discovery of gamma-ray flares from the Crab Nebula. Now, I should mention that the Crab Nebula also has a very special place in astronomy for high-energy astrophysicists. It's not only one of the very brightest and most interesting objects in the sky, it was thought to be the only true standard candle that didn't vary. And this work not only showed that that wasn't the case, but the results of the work were so surprising. They've had a very deep and fundamental effect on our research and our understanding of things like particle acceleration in objects. So without further ado, I'd like to present this award to Marco Tavani, along with our check that we provide for the award. Marco? Okay, now, let's see. So you do this from here, and so here's your mic, and hopefully it works.
Yes, it's a great honor, of course, for me to be here today, and we are going actually to talk about this extremely important object for high-energy astrophysics, which is the Crab Nebula, which is indeed, as you will see, what I'm calling actually the queen of nebulae, really a fantastic supernova that exploded in 1054, recorded, of course, by the Chinese astrologers or astronomers. And since then, really, at least for us, has been, in recent decades, sort of source of inspiration and of discoveries. Actually, let me just very briefly, in 10 minutes or so, give the sort of set the stage for understanding the excitement that we are having these days about these new discoveries. And Earl of Rosse, William Parsons, who actually named the crab from this sort of sketchy diagrams that he was making more than a century ago. You see, this actually looks more like a pineapple rather than a crab. Of course, like Virginia Trimble, indeed, already said that in a very beautiful paper about that. But he says it's an easy object. So you will decide by yourself at the end of this talk whether this is true or not. Okay. Let me say up front that we are really facing an extremely interesting phenomenon here, something which is unexpected. We, of course, have been studying particle acceleration in many contexts, and the crab offers a fantastic laboratory because we accelerate particles up to very high energies, up to PeV energies, 10 to the 15 electron volts for sure. But here we are witnessing something even more extreme, as you will see. Okay, something which was not predicted by our models, our idealizations. So definitely now we are going to learn something different compared to what we have been doing until now. And so the first 10 minutes of my talk, I will just set the stage, and then I will present the new results. Of course, it's an honor here for me to acknowledge the great contributions of the team, of the Agile team, but also of other teams, especially the Fermi team, of course, who really played a major role in this development, and our collaborators that you see their names there, and actually some of them are in the room, and I will mention their contributions in a few seconds. Okay. Of course, we are building on the work of many people, and Bruno Rossi was mentioned. I found actually just one slide from his lectures in the 70s. Of course, the Crab Nebula was a major system to consider for him. Actually, you see here the Einstein Observatory at the end here, at the right corner of this picture, the image of the Crab Nebula seen in X-rays by the Einstein Observatory. Now in a second, of course, you will see what we can do today, much more sophisticated, but definitely very intriguing already at that time. Okay, so this is my contribution to the Rossi understanding of the importance of this system. And of course, you see that the Crab has a central region where most of the action takes place, but also this diffuse emission of optical and radio emission that I will not have time to discuss, but it's also extremely intriguing and sort of mysterious also. So the central part, of course, is creating a lot of action, as you will see, because there is a neutron star rotating 30 times a second, generating a relativistic wind. And this actually action from the central part of the supernova remnant is affecting also the rest of the supernova. Okay, so this is very interesting. But let's concentrate on the central part of the nebula. So this is a Hubble image. The central dot here, you see the spot is, of course, the pulsar. And this is the X-ray image obtained by Martin Weisskopf and collaborators already several years ago. You see a very complex structure, a sort of toroidal structure, and some sort of rings and knots. Okay, indeed, the terminology of the people here also coupled with the optical features is that you have these so-called wisps, which are these sort of striations. You have knots, which sort of flickers, and also you have the so-called anvil, which is the base of some sort of strange feature that we call the southeast jet. Okay, so all these kind of things are going to be important the next minutes, so that's why I'm actually focusing on that. And I'm pretty sure everybody has seen this movie, and the only reason why I show it again is that really shows, without any words, really the beauty of this relativistic wind. You see that there is a sort of almost standing shock here that doesn't really move, but all the rest is quite variable. Okay, and that's very important for us. So the neutron star is very active in producing a relativistic outflows, definitely of electrons and positrons, and they are produced in the so-called magnetosphere that rotates very fast, and actually the outflow organizes itself in a very interesting way. So you have a sort of equatorial region where definitely you have a concentration of particles which form the torus that you have seen in the Chandra image. And then also you have another interesting region, that is a polar region, where in principle you might have also particles escaping from this part and producing a sort of pseudo-jet. Okay. And that's exactly the representation we have today. And this is important for what I'm going to say in a few minutes, because really the Crab is working not, as you see, in a symmetric fashion, but actually you have a concentration of outflow in the so-called torus, which forms the inner ring, which is shocked by the inner ring at some point. And then you have also the concentration of particles in these jets. Okay. Of course, the pulsar rotates and produces a wonderful electromagnetic spectrum from radio going to high-energy gamma rays. And of course, the signal is pulsed. I don't have time to talk about the pulsar itself. For me, it's just today a source of very energetic electrons and positrons and maybe ions. But just to mention the very recent excitement by Veritas and MAGIC experiments in DTV that together with the Fermi instrument, you see that they determine the spectrum. This is the pulsed spectrum that doesn't really have a cutoff, but actually extends up to hundreds of GeV energies. This is a very interesting, important discovery for people studying pulsars. I don't have time to discuss about this, but this is also in the background a very recent development. But the crab is very famous, of course, for the electromagnetic spectrum once you subtract this pulsar contribution. So this is what the people call the crab nebula spectrum. So you subtract the pulsar contribution and you end up with the radio, optical, soft X-rays, gamma rays spectrum. And the crab is very efficient in transforming the spin-down energy of the neutron star into synchrotron radiation, and has been used for decades as a standard candle, especially in the X-ray. So every time you have an X-ray new instrument in space, or even gamma ray, of course, in principle, you just look at the crab, because the crab is the perfect calibrator. Okay? It's a very bright source with known properties. If you consider also what happens at TV, this is a representation that in addition to the gamma rays, it's also, GeV energies also has the TV component. The TV component is interpreted as inverse Compton of particles which synchrotron radiate and produce, there is one population which takes care of the diffuse emission in the nebula producing the radio, and then there's another component coming from the most compact part of the nebula producing from the optical, the X-rays, and then the gamma rays. You see the gamma rays have this sort of strange cutoff here. And now we're going to, in a minute, to summarize why there is a cutoff there, and because this is the region where most of the action now will take place for surprises. It's interesting to see that this population which produces the X-rays and the gamma rays has this behavior. This is gamma squared times the differential number of particles as a function of Lorentz factors. You see that there is a region here where really you are running out of steam. Okay? And this is going to be important also to remember this slide, because this is where something happens at some point, which is interesting. So we have this understanding of an average magnetic field which is pretty large, 200 microgauss, that's why it's shining so well in synchrotron, and then the number of particles produced per second, and the total number of particles also more or less. These numbers provide a good model of the crab. So is it variable? Of course it is variable. The wisps and the knots that you have seen in the Chandra movie are flickering all the time. And also the pulsar has some radio glitches and giant radio flares sometimes. So there are some unconfirmed claims of also in the literature of some variation in the X-rays or gamma rays, but they were sort of controversial and not really confirmed. And I don't have time to talk about this, but I'm pretty sure everybody here in the room has some opinion about those. But let me just mention that this is a typical glitch behavior of the crab. You see that there is a difference in frequency occurring on a very short time scale, but there is no evidence at the moment connecting the activity from the central source to the activity in the nebula. Okay, so that's why for the rest of my talk I will not consider the pulsar anymore, and then I will just move on to the nebula. And the nebula is very rich in phenomenology. So we have seen the X-rays, this is the optical activity, and this is also the radio. So the nebula is very active. So the picture that we had since the great work of Kennel and Coroniti in 1984 is that there is a pulsar wind, which is at some point stopped by itself, by instabilities or by a shock, and then you have synchrotron emission and acceleration of particles coming at the inner region, okay, here more or less. And this outflow depends, of course, on many parameters. One crucial parameter is the ratio of magnetic field energy over the kinetic energy of particles. Okay? And the Kennel-Coroniti model works when this sigma parameter, so-called sigma parameter, is small, 10 to the minus 3, or 10 to the minus 2. So these are models of people working over the years with magnetohydrodynamics, you see that they reproduce pretty well some sort of a wisp-like structure of the nebula. So this is very successful. So MHD actually seems to work to some extent also to reproducing specific features of the nebula. And if I say that the acceleration indeed in these MHD models work like it is proportional to the cyclone frequency of electrons and positrons, then I end up with an equation which tells me the rate of acceleration and cooling, of course, and also balancing these two gives me a sort of maximum Lorentz factor. Okay? And this actually works pretty well, but this assumes, of course, in the standard model, the Jaeger and Harding, that the electric field and the magnetic field actually are related in this way. Okay, so really that their ratio is of order unity. But what happens if this ratio is not unity? This is, of course, not MHD. This is a very transient phenomenon, maybe occurring by magnetic field reconnection or by some, in any case, some parallel electric field that violates MHD. Then you end up with a different condition, of course, and in principle you end up with a number for the energy, maximum energy, which is larger than what you would have expected. And that's the maximum energy that you can get, actually, in photons, about 1 or 200 MeV. Okay, so this is a very conservative assumption, actually, of 200. And indeed, this is what you see in the standard spectrum of the crab. You see that this rapid cutoff that you see in the spectrum is interpreted as coming from this magnetohydrodynamic condition, okay, and assumptions about the acceleration coming from with the rate proportional to the cyclotron frequency. Well, is it the end of the story? Of course not. Okay, the crab is actually pretty rich, and we have two phenomena that we are facing today. One is, of course, the very rapid variation that we are facing now in gamma rays, that I will focus in the rest of the talk. But also there are some other slower variations that people noticed at the level of maybe 10% or 5%, whatever, also in X-rays. Okay, so the crab really is not the standard candle that we thought, even in X-rays. Okay. But before we get there, just a few seconds on the two great missions that we have at the moment. Of course, Fermi, you heard a lot about Fermi, also because it was the recipient of the previous Bruno Rossi Prize last year. Let me say a few words about Agile. So Agile is a small satellite compared to Fermi, but actually has many twists and many interesting features. Okay, so it combines gamma ray and hard X-ray imaging simultaneously. And there's a very different approach of pointing compared to Fermi. So the two missions really are providing a tremendous set of data just because they're complementary to each other. Okay. So there are three main features of Agile that I can summarize very briefly about the performance. One is that it is very well calibrated around 100 MeV. And this has been, since the beginning of Agile in 2007, a very beautiful source of data. Also, another interesting point is that the point space function, the imaging, the gamma ray imaging of Agile and Fermi are comparable. Okay, this is also a little bit of a surprise because they're very different, but actually it turns out that the PSF is very good. And also the final thing which plays a role in the case of the crab is that it has a very efficient ground segment, meaning that the satellite collects the data, downloads the data over Kenya, and then from Kenya we go down to our computers in about 2 or 3 hours. Okay, so and this is actually something that happened in the case of the crab flare. So it was extremely rapid data analysis. Okay. Here is the crab in galactic coordinates. You have the galactic center here. The nearby spot is the so-called Geminga pulsar. So now in the next few seconds you will see these two objects together and being studied. Indeed, this is what Agile did during the first 2 years and a half, pointed at the crab several times, and of course Geminga is nearby, so you catch both. And didn't see anything particularly interesting. Of course, the crab is a good calibrator. Okay. But at the beginning of the mission, the very first 2 months of data, when we looked at the crab first, we noticed that there was something very strange. Okay, this happened in 2007, and this created a tremendous amount of discussions and pain. Okay. Okay, then actually at the end of 2009, Agile stopped pointing, so could not point anymore, started actually spinning because of a malfunction of a reaction wheel. So that's why we, after having studied the crab with a few pointings, we started monitoring the crab for many, many months. And that's why at some point we ended up with this incredible rise again of the crab that we noticed in September 2010. And I tried to summarize the feeling that we had that night when we were going to issue this telegram. And this is the kind of... So the situation was pretty bad. So we were actually seeing, as you see, compared to Geminga, which is here on the left, we were seeing a variation of the gamma ray flux from this object, very dramatic, and something that, of course, we were not expecting, but something that we saw in 2007. So the psychology behind this was, in 2007, let's wait and see whether we see this phenomenon again. But we were breaking a taboo. The crab is not stable anymore. So you see that it was only 1 point. It was a very brief outburst, actually, lasting 2 or 3 days. Of course, immediately also Fermi saw exactly the same thing, clearly, and that created tremendous uproar. Everybody looked at the crab. There were very important observations by Swift, by XTE, and by Integral, and so on and so forth. Okay, so this is the spectrum that you see for the first flare, but from the very beginning, we noticed that there is a dichotomy of interpretation of the spectrum. You see that it's a gamma ray flux sticking out from the standard nebular flux by a factor of about 10 or so here in this range around 1 GeV. But then you have an interpretation that you could either have something very confined in energies, like a relativistic Maxwellian, like the blue curve, or something actually more extended, like a power law. Okay, so if you actually want to connect some of the Chandra knots, the Chandra spots in X-rays with the gamma ray flaring, you probably have to rely on a power law model with this red curve. Okay, so the issue of whether there is a connection between the X-rays and the gamma rays was from the very beginning very important. And indeed, we studied that with some observations taken a few days later of the first flare by Hubble and Chandra. And if you focus here on the right part, the bottom of this figure, you see that there are some spots by Chandra, especially source A, which is pretty promising, has been, of course, detected many other times in the past, but it was a sort of hint that maybe something might be related with the gamma ray flaring. Maybe yes, maybe not. So today we actually have 4 major gamma ray flares detected by Fermi and Agile. The rate is about 1 per year, more or less. Okay? And these are the events. Okay? So you see that are very different from each other. And also last July there was the last of these events actually announced. But it was actually of a smaller flux. Actually, this is Roger Blandford showing the light curve of the most recent event. At this meeting, we were actually gathered in Frascati just to talk about the crab, and by coincidence, the crab was flaring just at the time. So it was actually a lucky coincidence. But going back to the 2007 flare, you see how strange it is. Okay, so there is a sort of precursor lasting for a few days, and then a slow rise. Okay? And if you look at this with the 12-hour bin, light curve that Agile could do that in pointing. So you see that actually you can have, again, this feature of the spectrum sticking out from the canonical nebula spectrum. And sometimes you also have a very dramatic flaring lasting just a few hours, just 12 hours or so. Okay? Very dramatic. Okay? Of course, Fermi also has this event in 2009 in their database. And this is revisiting our discovery event of September 2010. It was one beam in the light curve I showed you a few minutes ago, but actually if you look in detail, it is a composition of actually 3 short flares lasting maybe 1 day or even less. Okay. So then we end this overview with this very major event in April 2011. Okay, so if you actually have now these 4 major flares, this is a sort of simple representation. You see how different they are. Sometimes they are very fast flares. Sometimes actually you have something which is not really a flare. It's a sort of rise, slow rise, and a sort of slow decay. So actually, in a recent paper, we call them flux waves. We run out of good names for that. I'm sorry, but it's a very interesting situation that, like the last event detected in this past July by Fermi, in addition to flares, which are these big events, you also have some other sort of enhancements which last on a longer time scale. We identified actually about 5 of these events, and this is a typical event in the Fermi database, which could also be confirmed by Agile whenever there is a similar and coincident exposure. So the energy of these events is about 10 to the 41 ergs, spread out over many days, or sometimes even, of course, a shorter time scale. And the efficiency, when you work out the efficiency from the spin down of the pulsar luminosity or energy, whatever, is about a few %. So there is a lot of energy involved in these events. Okay? And if you look in detail at the brightest of these events, which happened in 2011, the Fermi spectrum taken at the peak is extremely good. Okay, so really now we can really make a detailed attempt of modeling this emission just because of the quality of this. Okay, so, and again there is this dichotomy whether this goes down to X-ray energies with a power law or whether it is confined in the gamma ray range. Okay, and this is of course these 2 different models, either quasi-monochromatic behavior or a power law. Okay? But what is really dramatic is that this is in contradiction with the simple idealization of MHD or diffusive modeling that has been used until now. Okay? So E over B, which is a parametrization of our ignorance of the process, you may say, is larger than unity, which is of course a contradiction with MHD. And clearly this is something else going on, and also there is this issue of where it is going on in the nebula. Okay, so this has been the source of a lot of interest in recent years now, and you see again the pulsar and some mysterious feature called knot number 1, which is very close to the pulsar, and then the Anvil region. So this region now is being considered. And we were really lucky in April 2011 because of Rolf Bühler of the Fermi team, who had the guts at some point at the very beginning of the phenomenon, more or less here, to trigger a Chandra target of opportunity sequence of observations, of pre-assigned observations, which were supposed to indeed be about 5, and indeed you see 5 here. 1 actually turned out to be exactly at the peak of the gamma ray flare. This is, of course, a coincidence. It will never happen again. But this is a fantastic database, of course, now that you can use to really see whether there is any connection between X-rays and gamma rays. Okay. And this is the recent paper by Martin that is on Astro PH. This is the combined image of the observations. This is a little movie that actually Alan Tennant and Martin gave me some time ago. I don't know if it's still valid, but anyway. So the crucial date of the peak is actually the 16th. Okay. Here, 16th. So you see the usual suspects of knots that, of course, are flickering, but nothing really dramatic. Nothing really dramatic. No apparent strong relation between a very dramatic gamma ray flare and X-ray spots. Okay. So presumably, it is what we are seeing here is consistent with the spectrum not being a power law, but actually being concentrated in a relativistic Maxwellian or quasi-monochromatic kind of line, okay, here, which of course then when you convolve that with synchrotron becomes something a little bit wider. But this is very important from the theoretical point of view. Okay. So definitely standard MHD is not adequate to explain the spectrum in time scales, and we need something else. So, of course, there are many regions and many hypotheses being put forward, as you can imagine, so many people working on some ideas. Let me just summarize a couple of ideas. Okay. Of course, Doppler boosting, if you have a situation that actually has a concentration of emission, and then you can use Doppler boosting to enhance the flux, might help, but we don't really see a lot of Doppler boosting in the nebula. So it's a bit contrived to use that as an explanation of what we are seeing. Okay. On the other hand, you can have, of course, instabilities both in the jet region or even in the torus region. Okay. And that's exactly what now a lot of people are considering. Okay. So let me just mention this interesting hypothesis that is based indeed on magnetic field reconnection in current sheets by Mitch Begeman collaborators, where indeed you might have a strong electric field which is formed when magnetic field lines just tend to be together and reconnect. And even though the calculation is still in a preliminary stage, this is just a test particle calculation, so it's not a self-consistent calculation. But you see that the spectrum here that you can produce from the beginning of the phenomenon up to some sort of cooling could in principle explain the phenomenon. Okay, of course the calculation does not have a dynamic range to get to 10 to the 9th or even more of the Lorentz factors, but qualitatively this is interesting. So definitely this is something that has to be explored. Alternatively, you may have the torus. Okay, and the torus actually is the site where you have a current sheet of magnetic field lines which go in opposite directions, and you might have actually the formation of islands just because of tearing modes, which can work. And of course, when you're in the torus, you have to be careful that the size of your emission has to be pretty small to be consistent with observations, and so there are, of course, constraints which are pretty severe. But I think this is also something that, in principle, might be viable, and it would be very interesting in the future to see whether it can be studied at a sufficient level of being quantitative. Let me just say a few words about what we think is also another exciting possibility, which is instead doing this acceleration, very fast acceleration in the jet, okay, in the so-called southeast jet, which is not really pointing at us. It's about 60 degrees from us, but yet it is a very interesting site. We know that there is a lot of optical and X-ray variability there. And just the similarity with what we witness also in our laboratories, sometimes with plasmas, which are subjected to kink instabilities, I think that the possibility of having a particle acceleration induced by these instabilities is definitely something that needs to be explored in more detail. This opens actually a possibility of applying this yet not completely explored physics also to other systems. And that's why actually we are so excited about the crab. But this is a possibility, and let me show you in the remaining minutes what we have been doing also to model that, also for 3D magnetohydrodynamic simulations of the southeast jet. Okay, so this is an example of that with some reasonable parameters. You see, this is the famous sigma. It's not 10 to the minus 3 of Canale Coroniti, but it's actually a much larger number, which applies not in the torus but in the jet. And this is actually the strange looking jet from Chandra data at large distance. Here we are, of course, at the distance of 10 to the 18 centimeters. We are not really in the inner ring region. And this is actually a jet which changes shape, as Martin showed recently. In 10 years, the kind of curvature, which now is turning to the right, at least from my perspective, 10 years ago was turning to the left. Okay, so definitely there is a variation also at large scales of this southeast jet. What we are hoping to show is that exactly where the jet kinks, you might induce the conditions for magnetic field reconnection and acceleration. But this has to be, of course, demonstrated. Okay. In any case, you need a size of acceleration and emission which has to be pretty small, okay, because otherwise you run out in contradictions with the data. And so I think that this is a very exciting possibility. Of course, has to be demonstrated to be viable, but it's something that can be extremely interesting in the future. And let me summarize the theoretical framework, stating that what we are witnessing here is something quite amazing, in the sense that if you work out the radiation reaction that you expect from first principles, you end up with this equation here at the top, here with the maximum Lorentz factor, which is 10 to the 8 divided by the square root of b, where b is in Gauss. Okay, so b is about 10 to the minus 3 Gauss, in this case. So you end up with 3 times 10 to the 9. Okay. And that's actually something that is consistent with all the flares that we are seeing, and also of the waves, actually, that I just alluded to earlier. Okay, so this is something that has to be, of course, checked also for the future activity, but in principle is very exciting, because I don't see any other phenomenon, at least in relativistic astrophysics, which is so neat and produces actually maybe the most naive and crazy spectrum you can think of, like a monochromatic spectrum. And it has to be seen whether this, what I'm calling super acceleration compared to standard MHD, really is able to explain the phenomenology that we are seeing. But it is definitely a possibility, and also either kinking or tearing modes are definitely there to be studied. And if this is a diagram that shows the dynamic range of Lorentz factors for this component producing X-rays and gamma rays in the nebula, which is extended from 10 to the 5th, 10 to the 6th, up to a few times 10 to the 9. But you see that the flares and also these waves appear to be consistent with something which is much more concentrated. Okay. So this is, I think, something for the future, of course. So we have to see whether this applies really to other Crab nebula activities, or even maybe other pulsar wind nebulae, of course. And in any case, we are now reconsidering the transport of energy from the central source in the jet at large distance, and a dissipation not by a shock, but by internal instabilities producing very efficient acceleration. And this, of course, as you can imagine, has a lot of implications in principle, a lot of blazars that might be explained, even though the conditions are completely different, of course, there, because you don't accelerate to 10 to the 9th. But nevertheless, the physics of kinking and presumably accelerating, if that is the case, could be quite similar. So this could be quite exciting to see whether this, what we are learning from the crab once more can be applied also to other systems. And also, let me just mention here the connection with the plasma physics in our laboratory, because I think that there are lots of questions whether the efficiency of magnetic field reconnection that we see in plasma physics laboratories is good enough for astrophysics, whether you really accelerate particles or you just hit bulk motion or whatever. So really, I think there are lots of questions that we need to reconsider with our colleagues, and this also is a very beautiful link that we can strengthen now in the near future. Okay. So let me conclude then saying that the crab is very active, and Agile and Fermi will continue to monitor it. Actually, by the way, we just ended up these days with a new app for smartphones for the Agile data. So if you want in the future to look at some crab nebula gamma ray flares, you just use your iPhone, as I did actually in September 2010, when we just uncovered the first flare that we recognized as a flare. And there is also a Chandra beautiful monitoring of the crab that started in 2011. I understand also Hubble is, as much as it can, follows also the Chandra pointings, so this is very good. And there are also other observations. Keck is almost regularly also looking at the crab. And I know that there are many groups also working, of course, with radio telescopes, infrared observation, and so on and so forth. So crab is extremely popular now again, and it has to be, because we still have to solve a lot of mysteries. And let's not forget also TV telescopes. I didn't have time to talk about TV. There are some controversial TV claims that there was some variability. They were not confirmed, but definitely theoretically, it's not impossible to imagine that if you have a concentration of particles and then they see a very anisotropic environment just because they are focused in a very special way, they might produce even some TV flickering. So I think that in principle, the TV people should also keep looking at the crab. So definitely our queen of nebulae is a continuous source of inspiration and surprises and a lot of physics, and I'm pretty sure that this is not the end of the story. Thank you very much.
I'd like to thank Marco for a wonderful talk. And are there any questions that people have? We have a microphone and the technology to receive your questions. Okay, well, I have a question. So some of the plasma physics that you discussed are things that you might expect, at least some of them, would occur in the solar environment. And are there any indications that some of these models are can be confirmed or refuted by solar studies?
Well, of course, solar studies are very important in many respects, especially magnetic field reconnection has been studied in solar flares, but usually the solar environment is actually collisional, so that you have collisional MHD situation. And here, in the crab, definitely we are in a collisionless environment, so that even the magnetic field reconnection details are going to be a little bit different. So definitely the sun is an inspiration, but I don't think that the models can really be one-to-one compared. Yeah.
You noted that the monoenergetic model was favored by at least the fact that the Chandra data isn't showing any flaring. If that's the case, do the flares show any change in the energy of the monoenergetic, or is it always about the same energy?
Well, this is a good question. There is not too much change, to our surprise. We checked also I showed you both the flaring spectra lasting maybe 1 day or 12 hours, whatever, and also the other sort of wave-like spectra. They're a little bit different, but not different maybe by a factor of 2, but not by a factor of more than 3 or 4, whatever. So we were expecting sort of variety of gamma factors. Instead, we see something which is consistent with between 3 and 4 times 10 to the 9th. So it's quite so that's why it looks that there's a process that is accelerating to the maximum, and depending on the local conditions, the maximum can be either 3 or 4 or 5, 10 to the 9, but not much different from that.
Okay, so I have one final announcement after we thank Marco again. So those of you involved in high-energy astrophysics know that the fun never stops. And just following this, we have the from 5:30 to 6:30 in the Hyatt Long Beach Ballroom D, as in dog. We have a meeting named with such a boring name, the head business meeting, but we do that to hold down participation. Because anyone who knows, who's been there, knows it's just an absolute riot. And we're, in addition to announcing the Rossi Prize winner for the coming year and discussing some things of the upcoming head meeting, we're also going to try to deliberate on the essential ingredients in the first head-sponsored cocktail, the Crab Nebula. So I'll see you there.